Today, I will introduce Edge AI, an emerging technology that enables artificial intelligence to operate closer to where data is generated. The title of my presentation is Edge AI, enabling real-time, privacy-preserving, and reliable intelligence beyond the cloud. My analysis is framed by the 2025 Gartner Hype Cycle for Artificial Intelligence. In this presentation, I will explain what Edge AI is, why it matters, its current maturity, its strengths and limitations, and its innovation potential in areas such as smart manufacturing, healthcare, and autonomous systems. First, I would like to explain why Edge AI has become increasingly important. Cloud computing has played a major role in the development of artificial intelligence. However, cloud-based AI cannot meet every operational requirement. For example, some applications require decisions within milliseconds. Others involve private or sensitive data that organizations may not want to continuously transmit to remote servers. In industrial or remote environments, network connectivity may also be unstable. Edge AI addresses these limitations by moving selected AI functions from central cloud servers to local devices, machines, gateways, or nearby edge infrastructure. This creates three main forms of business value. First, it enables faster decision-making. Second, it reduces the amount of data that must be transmitted to the cloud. Third, it improves operational resilience when connectivity is limited or interrupted. Therefore, the core question of this presentation is, how can Edge AI create business value, and what barriers currently limit its large-scale adoption? To answer this question, we first need a clear definition of Edge AI. Edge AI refers to running artificial intelligence models on edge devices, local gateways, or nearby computing infrastructure, rather than relying entirely on remote cloud servers. It normally combines three functions: sensing the environment, processing data locally, and making decisions close to the data source. For example, a camera in a factory can capture an image, analyze it locally, and immediately identify a possible product defect. It does not always need to upload the entire video stream to the cloud before making a decision. The architecture shown on this slide contains three layers. At the device layer, sensors and cameras generate data. At the edge layer, local systems perform inference, filtering, and real-time control. At the cloud layer, organizations can still perform model training, central coordination, long-term analytics, and data storage. An important distinction is that Edge AI does not completely replace cloud AI. Instead, it distributes computation intelligently between devices, edge infrastructure, and cloud platforms according to latency, privacy, cost, and resource requirements. After understanding the technology, the next question is how mature Edge AI currently is. This slide presents the 2025 Gartner Hype Cycle for Artificial Intelligence, with Edge AI highlighted. The Gartner Hype Cycle describes how emerging technologies move through different stages of expectations, disappointment, learning, and productive adoption. In this diagram, Edge AI appears on the descending side of the curve, moving away from the period of extremely high expectations and toward more practical evaluation. This does not mean that Edge AI has failed. Instead, it suggests that organizations are becoming more realistic about what the technology can and cannot deliver. Several factors are increasing adoption. These include the growth of IoT devices and robotics, the demand for low-latency decisions, privacy and bandwidth concerns, more powerful AI accelerators, and the development of smaller models. However, Edge AI has not yet reached full maturity. Major barriers include device heterogeneity, limited memory and power, cybersecurity risks, complex model updates, and uncertainty about return on investment. My interpretation is that Edge AI is moving from hype toward practical enterprise deployment. However, large-scale adoption will depend on whether organizations can manage security, governance, device maintenance, and the full AI lifecycle. These opportunities and barriers can be examined more systematically through the enabling technologies and a SWOT analysis. Several technologies have made Edge AI increasingly practical. The first is specialized AI hardware, including GPUs, NPUs, and other accelerators. These processors allow devices to perform local inference more efficiently. The second is model compression and quantization. These techniques reduce model size and computational cost, making deployment possible on devices with limited memory and processing power. For example, FedFSFQ is a communication-efficient tuning approach that reduces the cost of adapting large language models across distributed edge devices. The third area is tiny ML and lightweight models, which support inference on highly constrained devices. Federated learning and edge orchestration also allow multiple devices to improve shared models without directly centralizing all private client data. On the right, the SWOT analysis summarizes the strategic position of Edge AI. Its main strengths are low latency, reduced bandwidth use, offline operation, and lower exposure of raw data. Its weaknesses include limited computing resources, energy constraints, and complicated model maintenance. The main opportunities are in manufacturing, wearables, autonomous systems, and smart cities. The main threats include cybersecurity attacks, regulatory requirements, device fragmentation, and uncertain financial returns. The key strategic point is that commercial success depends on more than model accuracy. It also depends on deployability, security, maintainability, and governance. These characteristics make Edge AI especially valuable in operational environments where decisions must be made quickly and reliably. One of the most promising application areas for Edge AI is smart manufacturing. A typical workflow begins with sensors or cameras collecting operational data. A local Edge AI system then analyzes the data and generates an alarm or maintenance recommendation when abnormal behavior is detected. This allows factories to identify equipment problems earlier, reduce unexpected downtime, and respond without waiting for cloud communication. As one representative research example, PGTMT demonstrates how an edge-based industrial IoT system can support early fault warning for rotating machinery through local and efficient computation. A second application area is healthcare and wearable devices. Wearables can continuously monitor physiological or behavioral signals, detect abnormal patterns locally, and provide rapid alerts. Local processing may also reduce the need to transmit all sensitive raw data to external servers. Third area is autonomous systems, including vehicles, robots, and drones. These systems require real-time perception and control. They cannot always wait for a cloud server because even a short network delay may affect safety or performance. From an innovation perspective, Edge AI can transform operational data into immediate local decisions. It can improve service speed, safety, resilience, and personalization. It may also support new business models such as intelligent equipment as a service, predictive maintenance services, and privacy-aware digital products. Overall, the strongest Edge AI opportunities are found in scenarios that are high frequency, low latency, privacy sensitive, and operationally critical. Finally, I will summarize the future direction of Edge AI and provide several recommendations for organizations. Looking ahead, Edge AI adoption is likely to increase as hardware becomes more powerful and energy efficient, while AI models become smaller and easier to deploy. However, the future is unlikely to be completely edge-only. A hybrid edge cloud architecture is more realistic. Edge systems can handle immediate local decisions, while cloud platforms support model training, coordination, storage, and long-term analytics. For organizations considering Edge AI, I have 4 recommendations. First, start with a high-value but relatively low-risk pilot project such as predictive maintenance or local quality inspection. Second, use Edge AI only when latency, privacy, bandwidth, or operational resilience creates a clear business advantage. Third, plan for model updates, device management, monitoring, and cybersecurity from the beginning. Fourth, continue using the cloud for tasks that require large-scale computing, central coordination, and long-term data analysis. To conclude, Edge AI does not replace the cloud. Instead, it extends artificial intelligence into the physical world by enabling faster, more private, and more resilient decision-making close to where data is generated.